Baris Kale and I am from Turkey. I graduated from Istanbul Technical University in 2014 as a mechanical engineer. Currently, I'm pursuing my PhD as part of a Baris Kale project called Zephyr, which has been funded by the European Union since 2019. In this PhD project, I focus on investigating the effect of realistic atmospheric conditions on the aerodynamic and aeroacoustic performance of wind turbines operating immersed in the atmospheric boundary layer. The characteristics of atmospheric flows change during a diurnal cycle. For example, in daytime conditions, the surface of the Earth is heated by the sun and atmospheric turbulence is triggered when buoyancy forces start to dominate shear forces. In contrast, shear forces become the dominant mechanism of atmospheric turbulence at night due to the cooling of the Earth's ground. This dynamic mechanism has a profound impact on the aerodynamic and aeroacoustic response of wind turbines, as these large machines operate within the lowest part of the atmospheric boundary layer that is in direct contact with the Earth's ground. Our atmosphere is a multi-scale environment and includes various atmospheric processes. It also involves a wide range of atmospheric scales that are important for wind energy applications, starting from mesoscale that are in the order of tens of kilometers, down to a few meters at microscale levels. Therefore, in order to explore the atmospheric boundary layer flow wind turbine interaction, the use of atmospheric flow solver coupled with a high-fidelity large eddy simulation solver and wind turbine parameterization is essential. For that reason, we have implemented two different wind turbine parameterization schemes, the generalized actuator disk and generalized actuator line models, into a numerical weather prediction model called the Weather Research and Forecasting Large Eddy Simulation Solver. In addition, we have also implemented the aerodynamic features of the wind turbine nacelle and tower, as well as several wind turbine control mechanisms such as speed and blade pitch controller and a wind turbine yaw algorithm in order to model a real wind turbine accurately. This mesoscale, microscale and wind turbine coupled flow solver allows the wind turbine wakes to be captured under realistic atmospheric conditions and to analyze the aerodynamic load and power output of the wind turbine at a particular location and time frame. So far, we have tested these mesoscale, microscale coupled wind turbine models in uniform flow conditions in flat terrain and under varying atmospheric conditions in flat and complex terrains respectively, and validated them against the results from available LES codes and experimental data from different field campaigns. We have concluded that our models are able to predict the wake behavior and aerodynamic performance of the wind turbine in terms of power output, as well as aerodynamic thrust and torque. As a final step, we have developed a methodology to account for non-uniformities in the atmospheric flow in predicting the near-field noise of a wind turbine operating under real atmospheric flow conditions. Since noise emitted from the trailing edge of the wind turbine blade generally dominates the entire aerodynamic noise spectrum, we have focused on estimating the trailing edge noise when determining the overall noise of the wind turbine. To do so, we have utilized the time series of the local angle of attack and relative velocity from our mesoscale microscale coupled generalized actuator line model. We have performed a set of Reynolds average Navier-Stokes simulations to extract the turbulent boundary layer parameters to be used as inputs in the semi-analytical ambient model for trailing edge noise modeling. The next step is to compare the noise estimates from the methodology that we have developed with the available experimental data from a field campaign.